welcome to Lecture 3 of Unit 5 Sequential Building Blocks. In this lecture, we're going to discuss shift registers with serial load and parallel load, universal shift registers, ring counters, Johnson counters, and the 74LS95 shift register IC. Let's start with shift registers. So a shift register is a register capable of shifting the binary information held in each cell to its neighboring cell in a selected direction. So it consists of a chain of flip-flops in cascade with the output of one flip-flop connected to the input of the next flip-flop. All flip-flops receive common clock pulses, which activate the shift of data from one stage to the next, or from one flip-flop to the next. So this is one of the simplest configuration using cascaded D flip-flops. So this is what we call a unidirectional shift register. There's only one direction of shifting, which is from left to right, and this is what we call a shift right register. So each clock pulse shifts the content of the register one bit position to the right, and this configuration does not support the direction of a left shift. So a serial input determines what goes into the leftmost flip-flop during the shift, and sometimes this is labeled as SI. And at the rightmost, since this is a shift right register, the serial output is also taken from its rightmost flip-flop. This is also sometimes labeled as SO. So serial transfer is one of the applications of where shift registers are usually found. So the data path of a digital system is said to operate in serial mode when information is transferred and manipulated one bit at a time. Information is transferred one bit at a time by shifting the bits out of the source register and into the destination register. This type of transfer is in contrast to parallel transfer, whereby all the bits of the register are transferred at the same time. The serial transfer of information from register A to register B is done with shift registers. So this is an example of a serial transfer from register A to register B. So let's say shift registers A and B have 4 bits each. And there is a control unit or a controller that supervises the transfer of data to enable the shift registers through the shift control signal. So this input here, shift control, determines when to shift the registers. Here, serial output SOA is connected to the serial input of register B, here labeled as SIB. To prevent the loss of information stored in the source register, which is register A, SOA is connected to SIA so that the information shifted out from register A is made to circulate back into register A. The initial content of register B is shifted out through its serial output, hereby labeled as SOB, and is lost unless it is transferred to a third shift register. The shift control input, again, determines when and how many times the registers are shifted. So this works somehow like an enable input. So for illustration here, this is done with an AND gate that allows clock pulses to pass into the clock input only when the shift control is active. Since this is an AND gate, it means that shift control must be 1 for the clock to pass through the clock inputs for both shift registers. So in actual circuits, this practice can be problematic. This is what we call clock gating. So this practice can be problematic because it may compromise the clock path of the circuit. This is especially true if we are designing synchronous sequential circuits. But for illustration purposes here, let's just consider this scenario. So considering the previous configuration wherein we keep clock gating here, So let's consider this timing diagram. So this clock here, showing this train of clock pulses, is referring to the clock input connected to the AND gate. The shift control is coming from a control unit or a controller that would determine how many times the shift register needs to shift. In this case, since we are considering 4 bits each, then the controller would only allow the shift register to shift out 4 times. And this clock here, CLK, is the output of the AND gate that is connected to both shift registers. So the controller or the control unit that is in charge of the shift control would send out a pulse which is just enough to transfer 4 bits of information. So in this case, let's take a look at this point. This is the sampling of what will happen after a certain negative edge. So since this shift control is 0, then the clock output CLK would be 0. On the next negative edge of the source clock and sampling the value of the shift control, then the clock gated circuit was able to produce one pulse here called T1. Then on the next 3 instances, we were able to produce 3 more clock pulses, T2, T3, and T4. After which, the clock is back to 0 again because the shift control is now 0. With this particular scenario, with 4 clock pulses, then this CLK clock would be in charge of synchronizing the shifting of registers A and B. So, for example, the initial value of register A is 1011. After T1, the previous one here is shifted into register B. And S0 of register A is looped back to the shift input of register A because of this configuration. So 1 is transferred here and the rest is shifted to the right. After T2, SO here is shifted into register B here and is shifted back into register A. So here. And everything else is shifted to the right. And this would happen for 4 clock pulses because there are 4 clock pulses fed to shift registers A and B. So again, this works, especially if we use clock gating. However, this might produce some inconsistencies because of the compromise we have done with the clock path. So again, this is not recommended unless you know what you're doing. The alternative is to use synchronous clock for all the components that you are using and just select shift registers with enable inputs. Now let's go to another application of shift registers. So we have here serial addition. So operations in digital computers are usually done in parallel because that is a faster mode of operation. Serial operations are slower because a data path operation takes several clock cycles. But serial operations have the advantage of requiring fewer hardware components. If you have an IC with limited space, using serial operations would have the advantage of requiring less silicon area on the chip. To mitigate the slow serial operations, another alternative is to use a faster frequency or a faster clock frequency. To demonstrate the serial mode of operation, here is a design of a serial adder. In this scenario, 2 binary numbers added serially are stored in 2 shift registers. So we have here shift register A storing the augend, and we have here shift register B storing the addend. Starting from the LSB, so at the rightmost part, so we are here considering shift right registers. So starting from the LSB, the circuit adds 1 pair at a time through a full adder circuit, here represented by FA. So the shift output of registers A and B are being added together as two significant bits in the full adder. Now the carry out of the full adder is transferred to a D flip-flop, where its output is then stored as the carry input for the next pair of significant bits. So here you can see that the carry output is connected to a D input, and the output of the D input is being connected to the third input of your full adder. So therefore, representing the carry input of the next set of numbers or the next set of bits to be added. The sum output of the full adder could be transferred into a third shift register, or we can also reuse shift register A by connecting S output here to the serial input of shift register A. By reusing shift register A, this would serve now as an accumulator. So the sum is stored back into shift register A. So the shifting process continues until the shift control is disabled. So here, take note that shift registers A and B have their own shift control or shift enable inputs. So here, shift control is connected directly to the enable inputs of shift registers A and B. However, for this D flip-flop here, there is no enable input. So there is no other choice but to gate the clock here. So the clock is being ANDed together with the shift control input. Therefore, this output of the AND gate here controls the clock for the D flip-flop. This serial adder here is a sequential circuit. So let's consider designing a serial adder using a state table this time, just like what we did in Unit 4. So here are some assumptions. So two shift registers are used for storing the binary numbers to be added. So that was shift register A and shift register B. Serial outputs from the registers are designated as X and Y, which would be the two bits to be added into our full adder. The sequential circuit to be designed will not include the shift registers, but they will be inserted later to show the complete circuit. An output S generates the sum bit, and a flip-flop Q is used to store the carry output. And the carry output, which is stored in the flip-flop, would be used as the third bit to be added together with X and Y. So using the procedures you have learned in Unit 4, we have here the state table. So the present state Q represents the carry input. Inputs X and Y is coming from the serial outputs of the shift registers A and B. On the right side, we have here the next state, which represents the carry out. The output S represents the sum. And to complete our design, we need to configure or find out what are the flip-flop inputs J and K for flip-flop Q. And for this one, we need the help of the JK excitation table. If we have here 3 combinations of input variables, then we need 8 input combinations. That is from 0, 0, 0 all the way to 1, 1, 1. And by adding all 3 bits, we are able to come up with this sum and carry outputs. Since we already know the present state and the next state, we use both bits so that we will know what caused that transition by knowing what J and K values are. And for that, again, we use the excitation table. So for example, this is 0 and this is 0. Then we must have 0 for J and K must be X. That's why we have this value. And if we use each present state and each next state and look it up in our excitation table, then we can complete this set of J and K inputs. So here are the simplified equations. We have the J and K flip-flop inputs, and we have here the output S. So if we considered a D flip-flop for present state and next state Q, then the result of our circuit would be the first serial adder example shown in the previous slide. So since we are using a JK flip-flop, here is our logic diagram. So the two shift registers are now added to complete our serial adder. So remember that X and Y comes from the serial outputs of shift registers A and B. So we still have the clock and the serial control inputs. So using the simplified functions, we can come up with the J input, the K input, and the sum output. And the sum is being connected back to serial input, while we are still clock gating shift control and clock signals so that we can control the clock pulses sent to the JK flip-flop. So far, our previous examples and scenarios are showing what we call unidirectional shift register. So this is a register capable of shifting only in one direction, either shift left or shift right. A bidirectional shift register, on the other hand, can shift in both directions, shift left and shift right. A universal shift register is another kind of register that has the ability of shifting, so either shift left or shift right, and it has what we call a parallel load capability. So parallel load capability means that we don't need to shift in and shift out to store an n-bit information into the shift register. We just use the parallel load capability to input all the bits that we need into the shift register. So the most common shift register has the following capabilities. A clear input to clear the register to 0. Next, a clock input to synchronize the operations. Number 3, a shift right control to enable the shift right operation. And together with that, we need a serial input and serial output associated with the shift right. Next, a shift left control to enable the shift left operation. And with this, we also need a serial input and a serial output for the shift left. A parallel load control for number 5 is to enable a parallel transfer, and we need n number of input lines. If we have a parallel input, then we must have n parallel output lines. Number 7, a control state that leaves the information in the register unchanged in response to the clock. So which means that even if there is a clock pulse supplied to the shift register, then the control state would allow the register to remain unchanged. So this might be in the form of a shift enable or a shift control. Now in this case, if this feature is available, then we don't need clock gating to control the number of shifts. So this is an example of a 4-bit universal shift registers. This is the block diagram, and this is its corresponding function table. So the function table would enumerate the register operations associated with this type of universal shift register. In this particular case, we have 4 modes of operations. We have no change, shift right, shift left, and parallel load. And this is controlled by what we call a mode control inputs. We have S1 and S0, and this particular set of combinations would enable this set of operations respectively. So this is its corresponding block diagram. So we have the clock input here, CLK. This is the clear control input to clear the clock register. We have here the control inputs to control the mode of operations. Since we have a shift right, we have here the MSB in or the shift input for shift right. since we have a shift left, this is the shift input for the shift left operation. And finally, since we have a parallel load operation, then we need 4-bit parallel inputs. Likewise, we also need 4-bit parallel outputs. 4 bits because this is a 4-bit universal shift register. So remember that the simplest configuration for a shift register is by cascading flip-flops. The simplest type of flip-flop would be the D flip-flop. So if we are going to connect or cascade the D flip-flops, we can have a unidirectional shift register. However, in this particular case, we have 4 different modes. So we need to select one of these 4 operations based on this mode control. So therefore, we're going to need a multiplexer. And since we have 4 register operations here for this universal shift register, then we need 4x1 multiplexers. So this is a brief overview of the logic diagram for the 4-bit universal shift register. Before I will show you how to design this type of universal shift registers, I just want to point out these points. Since we are designing a 4-bit shift register, then we need 4 D flip-flops. And since we have 4 different modes of operation controlled by S1 and S0, then we need 4x1 multiplexers. And the number of 4x1 multiplexers depends on the number of D flip-flops. And so, since we are designing a 4-bit shift register, then it is natural to have also 4x1 muxes. And take note that the multiplexers are connected directly to the D inputs because the selection is done in the multiplexers, and after the selection of operation, the output is directly fed to the D inputs. Now for the solution, let's switch to the whiteboard. So again, since we are designing a 4-bit universal shift register, then we have here 4 D flip-flops. And together with the 4 D flip-flops, we must have the 4x1 multiplexers here. Again, the size is determined by the number of operations, which we have noted here. So this is 00 for no change, 01 for shift right, 10 for shift left, and 11 for parallel load. Before anything else, you have to make sure that the clock is synchronous to all the D flip-flops. So in this case, the clock source is supplying every single clock input of our D flip-flops. And likewise, we have the clear input here as a direct input controlling the clear inputs of every single D flip-flop. For the multiplexers, S1 and S0 is connected to the selectors of our multiplexers. So these are common selectors, so which means that all the selectors of the muxes are connected to the same S1 and S0 source. So just think of this as connected underneath the multiplexers. So anyway, what we must first do is the output of the multiplexers must be connected to the D inputs. There. Next, using the mode control inputs, we need to support this set of operations. Let's take first no change. To enable no change, we must use input I0 since this is 00. So I0 are here, indicated by the 0 labels in the multiplexers. So no change means whatever the present value of Q is the next state value of our D flip-flop. So that means that we need to take Q and connect it directly to I0. There you go. So forgive the messy lines. So this is also I0. This is also I0. And lastly, the last flip-flop. Next, we are going to support shift right. And this is done when we have 1, 0 at S0, S1. So this is I1 in the multiplexer, input 1. So we have this. So we are shifting in the right direction. So let's consider this layout, and this is shifting to the right. So this is the leftmost. So this must be where the serial input comes in for shift right. So we have here serial input for shift right. And since the input of Q here must be shifted to the one at the right, then we can use this input. This is connected to Q and connect it to its neighboring D flip-flop, which is connected to this neighboring multiplexer. Next, this Q here is shifted to this D flip-flop. So take this input Q and connect it to 1, input 1 of the next one to the right. This one as well. And the rightmost flip-flop, its Q at least, is now our designated serial output for the shift right operation. Don't forget these labels. Now let's go to the next, SL or shift left. And this is supported by I2 input of our multiplexer, 1, 0. So I2 is here. Now, since this is shift left, we go in this direction. Shift left. So we start at the rightmost. So this is our, let's just use this one. Shift input for left. Okay. Now, the output of these Q is connected to the input of its left neighbor. Then we go to the next flip-flop, connect it to input 2, I2. Next, this is connected to input 3. And since this is the leftmost flip-flop, then this must be our shift output for left. And finally, we have our parallel load supported by 3 or I3. So parallel load means we have 4 bits, so we need 4 parallel input lines. So we have this one. So let's just call this as parallel input. Let's say this is 0. This one is parallel input 1. This is parallel input 2. And this is parallel input 3. You can have any names here. And likewise, since we have inputs, we must have parallel outputs as well. So this is our parallel output 0. This is our parallel output 1. This is our parallel output 2. And this is also our parallel output 3. So this is our complete block diagram for our 4-bit shift register. So going back to our slide, this shows a clearer version of our design. So the only difference here is that we might have a different layout of our inputs, but that is okay, just as long as you label them correctly. Likewise, we have different labels also for our parallel outputs and parallel inputs. So to briefly verify our design, this is showing you a Proteus simulation file. In this particular case, I'm using 74 LS76 flip-flops. So these are JK flip-flops. And these are configured to work as D flip-flops. That's why we have here J is connected directly to the multiplexers, the output of the multiplexers, and the K inputs are the complemented values of the multiplexer outputs. So this now functions as D flip-flops. To represent the 4x1 multiplexers, I'm using two 74LS153 ICs, and this contains two 4x1 muxas, and the second one also has two 4x1 muxas, so a total of 4 multiplexers. So I have here the clock input connected to all the flip-flops, in this case all the D flip-flops, and the preset input or the direct set inputs are disabled, and the clear inputs are controlled by this switch. The outputs of all the flip-flops are connected to 4 LEDs, and we have here two dip switches. The first dip switch at the left side represents the shift input for shift right. The second one after that is the SIL or the shift input left. The last two here are the mode control inputs S1 and S0 connected to the selectors of the multiplexers. On the second dip switch, these are the 4 parallel load inputs. And likewise, we also have the parallel load outputs here connected to the flip-flop outputs. And likewise, if we have SIR, we must have SOR. And if we have SIL, then we must have SOL here. So just to briefly show you the operation. So let's clear our circuit. And let's see. Mode is 0, 0. Then this is no change. If we have here a 0, 1, then we shift to the right. So let's use the shift input. So you can clearly see that 1 is being shifted into the shift register. If we bring SIR to 0, then we are shifting zeros. So let's say, let's have parallel load 1, 1. So whatever the inputs here in our parallel inputs, it is being loaded into our shift register. And finally, we have 1, 0 as shift left. So we use SIL input. We are shifting 1 into our shift register. And if we bring this to 0, we are shifting zeros. So this is our 4-bit universal shift register. So moving on to the next topic, we have another application here, what we call ring counters. So this is a special type of a counter, as its name. So it is a circular shift register with only one flip-flop being set. Set means we have output 1 at any particular time, and all others are cleared. If you say cleared, 0. The single bit is shifted from one flip-flop to the next to produce the sequence of timing signals. So producing a sequence of timing signals is one of the main goals of the ring counters. So this is an example of a shift register implementation. So this is a 4-bit shift register, and we are operating at the right direction. So this is a shift right. So this is the control, and we have here T0, T1, T2, T3. And take note that these are the parallel outputs of our 4-bit shift register. And in this case, this is the output of our ring counters. So take note that we are shifting to the right. And the rightmost bit, our shift output right, SOR, is connected to our shift input for shift right operation. So this is SIR. Since a ring counter has one flip-flop being set, so let's consider this initial value 1000, this being T0 having a value of 1, and the rest are zeros. So if we have this particular sequence, T0, let's say output A, T1 output B, T2 C, and T3 as E, then we have here 1000. After one clock pulse, we go to the next sequence. So 1 is being shifted to the right. Now it is at B, and the rest are zeros. At the third sequence, the next clock pulse, the 1 at B is being shifted to the right. Now goes to C. And on the fourth one, the 1 at C becomes the 1 at flip-flop E. And this goes through 4 sequences, and if we have more clock cycles, then this just repeats. So this is the timing diagram of our ring counter. So we have here our clock pulses. We have here T0 as having the 1 at a certain period of our clock. On the next clock pulse, this 1 is being shifted to the right, here now at T1. On the next clock cycle, the 1 is being shifted into its rightmost flip-flop, which is at T2. After the next clock cycle, that 1 is being transferred at the rightmost part. And the sequence just repeats itself. So an alternative implementation, instead of using shift registers, is by using a counter and a decoder. So in this case, we have a counter. So we have a count enable. And since this is having 4 bits at the output, then we need a 2-bit counter. So this is counting from 00, 01, 10, and 11. And these counter outputs are being connected to a 2x4 decoder. Now remember that a decoder may have unique 1s or unique 0s at the output. So in this case, let's just assume unique 1 outputs. So which means that if our counter here is 00, we have a 1 at our T0. If this is 01, we have a 1 at T1, and so on. So for either implementation, whether using a counter and a decoder or using a 4-bit shift register, then each flip-flop or each decoder output is in the high state or 1 state once every 4 clock cycles and produces one of the 4 timing signals as shown here in the timing diagram. So another application that we have for shift registers are what we call Johnson counters. So a Johnson counter is a circular shift register, very much like the ring counter. However, with the complemented output of the last flip-flop connected to the input of the first flip-flop. So the designation where the last or the first flip-flop is depends on the direction of the shifting. So this is also known as a switch tail ring counter because of the complemented output. And an n-bit Johnson counter produces 2 n timing signals. If in our previous example, we have a 4-bit ring counter, the number of timing signals is also 4 signals. So there is a direct proportion to the number of bits to the number of timing signals produced. In the case of a Johnson counter, we can have twice more timing signals. So if we have in this example, let's take a look at this. We have 4 D flip-flops, so which means that this is a 4-bit Johnson counter. And this 4-bit Johnson counter produces 2 times 4 or 8 timing signals. So let's consider first the configuration. So this is the shift right Johnson counter because of the way the D flip-flops are cascaded. So output of the leftmost is connected to its neighbor at the right. So this is A connected to DB. The output B is connected to DC. The output of C is connected to DE. And take note of the last flip-flop. We have here the normal output E. But since a Johnson counter takes the complemented output, so we also have to connect to the complemented output of E, which is E prime. This is connected to the shift input we have at our first flip-flop, which is DA. Now to synchronize the operations, don't forget that the clock source is the same for all the flip-flops. So to simulate the output of our 4-bit Johnson counter, let's take the initial value of zeros for all the flip-flop outputs. So this is 0, 0, 0, 0. On the next clock pulse, since we are shifting in the complemented output E or E prime, so that means that we are shifting 1 into our Johnson counter. So this becomes now 1, 0, 0, 0, shown here in sequence 2. On the next clock pulse, we are still connected. The serial input here is still connected to E prime. So that means this is now 1, 1, 0, 0. So we have here sequence 3. On the next clock pulse, this now becomes 1, 1, 1, 0. So here sequence 4, 1, 1, 1, 0. On the next clock pulse, this is now all ones, 1, 1, 1, 1. Shown here in sequence number 5. Now, since we have here the last output as 1, E is equal to 1, then E prime must be 0. So, on the 6th sequence, we are shifting in 0 into our Johnson counter. So, this is now 0, 1, 1, 1. Shown here in sequence 6, 0, 1, 1, 1. On the next clock cycle, this becomes 0, 0, 1, 1. On the next, this is 0, 0, 1, 1. And on the 8th sequence, this is now 0, 0, 0, 1. And since this is now 1, E prime must be 0. So on the next clock cycle, this becomes 0, 0, 0, 0, which brings us back to our first sequence or our initial value at the start. So take note that we have 8 sequences here in our flip-flop outputs. So each combination of our flip-flop outputs are unique. And to produce the 8 timing signals, then we need to decode them using an AND gate required for the outputs considering these particular configurations. Now this is based on the uniqueness of the output values. So take note of the first sequence number. This is A prime, E prime. So this means that we are taking A, which is 0, and E, which is 0. So that's why we had the prime here for both variables. And if we look at the rest of the columns A and E, there is no the same sequence 0, 0 for the other sequence numbers. So that would decode our first timing signal. For the next, we have A, B bar. So this is considering A, which is 1, and B, which is 0. On the next, we are ANDing B and C prime. Next, we have C, E prime. Next, we go at these two outputs here again. But this time, this is 1 and this is 1. So this is A and E. Next, this is A prime B, this is B prime C, and this is C prime E. So this would produce our 8 timing signals. So if we need to produce 8 timing signals for our 4-bit Johnson counter, then we need to add this decoding gates into our outputs. But in the case that we don't need to show the timing signals, then this completes our 4-bit shift right Johnson counter. Now let's go to an actual shift register. So we have here the 74LS95 IC, which is a 4-bit shift register. So this is with serial and parallel synchronous operations. So this is the pinout of our 74LS95 IC. And take note that this might have a different naming configuration with the one we're going to use in Proteus. So here is the function table for the IC. So we have the following operating mode. So technically there are just 2 of them. We have shift right and parallel load. So this is controlled by the mode input and having 2 separate clock sources for each of the operating modes. We have a serial input for our shift right, and we have 4 bits as our inputs in our IC, namely A, B, C, D, which is for the parallel load, and we have the outputs QA, QB, QC, and QD here at the right side. So take note that considering the first operating mode, shift right, we need the mode to be low, so mode must be 0. So since there are 2 clock sources and the other one is just don't care, we can just connect them both to the same clock source, meaning we can tie them both together and it won't affect the operation. So going back, for the shift right, SER input found here at pin 1 is our shift input or SIR. And for the shift right, we don't need to consider inputs A, B, C, and D. And the direction of our output is from A to QD. If we have here serial input as low, on the next clock cycle, that input would be reflected in QA. The rest of the bits are being shifted to the right. If we have serial input as high, then high is reflected on QA on the next clock pulse, and everything again is being shifted to the right. For parallel load input, we need the mode to be high. And since we are connecting both clock inputs to the same clock source, then it won't matter at this point. Serial input is don't care because we are using the parallel load inputs A, B, C, and D to load our data in parallel mode into the shift register. So the only way we can support shift left in this kind of IC is to use the parallel load configuration. So what we do is we take the parallel load configuration, which is mode is high. The clock inputs, we can just tie them together. The serial input is don't care. And what we do here is we manually connect the output of the flip-flops to our parallel inputs. So which means that our serial input for left direction or SIL must be at D, so here. And the output of D is connected to C. The output of QC is connected to B. The output of B is connected to A. And QA is our serial output left or SOL. So let's take a look at a few examples. So the first one, using 74LS95 ICs, we create the first one, a 4-bit shift right register. So let's design our 4-bit shift right register. So using 74LS95 IC, So let's follow the shift right configuration. So using the shift right mode must be low. So this must be connected to ground or low. So since we are using block diagram, let's just put some symbols here to simplify our solution. Now for our clock inputs, to simplify the design, we can just tie them together on the same clock source because anyway, this second clock is just don't care. Next, since this is shift right, we need to use the serial input, so SER. So again, this might have different names in Proteus. So this is our shift input right. And lastly, these are don't cares. So this can be connected to ground or connected to high. And since this is shifting to the right, then shift right goes into that direction. So this is the first LED, the second, the third, and this is our fourth or the last flip-flop, which is our serial output right. And so to complete our design, so it's always better to just not leave the input pins hanging. So maybe we can just tie them all to ground. Anyway, we don't need these inputs for this particular problem. So this completes our design then. So to quickly verify our design for example 1A, so we have here the 74LS95. Please take note that we may have different naming configurations for the pin names, but you can always reference them with the pin numbers because the pin numbers will always remain the same. So we have here a switch connected to the serial input SI in this case and SER in the case of our function table. And we have here the two clock inputs and they are tied together on the same clock source. The inputs in the case of our previous design, we have this as A, B, C, D, and we just simply put them to ground because we don't need to use them at this point. And the mode is also low, that's why this is connected to ground as well. So the outputs, we have Q0, Q1, Q2, Q3. These are QA, B, C, and D respectively, and the direction is in this order. So in our notes, it was in our initial design, we have here starting at Q0 and we shift right towards Q3, and in this case towards D4. So since we have serial input, we must have a serial output at the rightmost flip-flop output, which is D4 in this case. I've also inserted some logic probes here for easier checking of our outputs. So let's run the simulation. So we have here logic zeros as seen here, and the LEDs are not turning on. So here we can see that the clock inputs are receiving clock pulses from the clock source. So the moment we close the switch, we are shifting in 1 into our circuit. And if we open the switch again, then we are shifting in zeros. And since we only need 4 bits, then one 74LS95 IC is sufficient. So taking a look again at the operating modes, we have here shift left, and in the function table, we don't have originally a shift left operation. However, we can manually perform a shift left using the parallel load. So again, the clock source or the clock inputs, we can just tie them up to the same clock source. To enable our parallel load, mode must be high. And then we don't care for our serial input, but let's just tie that to ground, giving it a low. Now we perform the shift left operation. Now again, we don't have a shift left here in this particular IC, but we can do so by using the parallel load inputs. So which means that in the shift left direction, we must go from QD to QA. So in that direction, that is the shift left operation. So which means that our shift input must come from the rightmost, which is D. So this is our shift input. Its flip-flop output is QD. So to shift the contents of this to the next flip-flop in its left neighbor, then we must connect this manually to our input C. The output of C is connected to our input B. Our output B is connected to our input A. And finally, our QA output here is our shift output. So if you want to be specific, you can put this as SIL and SOL. But in this case, there's no need because this is only a unidirectional shift register, shifting to the left. So let's use Proteus again to quickly verify our design. So we have here the 74LS95 IC. We have here our clock inputs tied again to the same clock source. We are putting mode to high in this case. And our shift input is connected to D3 or the rightmost flip-flop. In the case of our manual design, this is named as D. Input D. So here. And our Q3 is connected to input D2. Our output Q2 is connected to D1. Our Q1 is connected to our input D0. And the leftmost output, which is Q0 in this case, is now named as our serial output or shift output, SO. Let's simulate. So normally this is just zeros as an initial state, but in the case of registers, once you turn on your power in an actual circuit, this can have any values. So anyway, let's try to shift in some ones. So this is now shifting to the left. If we shift in zeros, shift in one again, so you would see some changes in our outputs depending on the value of our shift input. So next we have here example 1C. So this time we now have a 6-bit shift left Johnson counter. So since the 74LS95 IC is just 4-bit, so therefore we need 2 of them so that we can meet the 6-bit requirement here. So here we now have our 2 74LS95 ICs, and we have to identify which one is in the leftmost part and the rightmost part. And don't forget that now we have 4 clock inputs, and all of them must be tied to the same clock source because we want them to be shifting in synchronous with the same clock. So let's start with identifying the shift left direction. So again, there is no shift left in the original function table, but we can do so using parallel load, which means that we shift in this direction. So we need to identify which one is the rightmost and the leftmost. So I think it's easier if we start here, in my opinion. So since we only need 6 bits, then we don't need all the 8 outputs. So here, let's start with identifying our shift input. So we have here B. And we are going to identify QA as our shift out because it's at the leftmost. Again, let's not forget the mode. So since we are shifting to the left using the parallel load mode, then we must set this to high. And it must apply to both ICs. Okay, so now let's start shifting. So this is the serial input or the shift input. its output QB must be sourcing our A input on our second SN4LS95. Then our QA must be connected to D input. Our QD is connected to our C input of our first 74LS95 IC. So I think you can do a better job than me in forming these lines. So anyway, what's important here are the logical connections. So QC is connected to B in our leftmost SN4LS95. QB is connected to A input. Now, this may be enough if we are just designing a 6-bit shift left register. However, in this case, we are creating a Johnson counter. So which means that the last output must be complemented so that we can form the switch tail ring counter or the Johnson counter. So which means that our last output, which is we identified here as SO, must be complemented. So since we don't have complemented outputs of our 74LS95 IC, then we need to use an inverter. So let's just put it here. This is our inverter, and we connect it back to our B input, which was what we labeled as our shift input. And all other unused inputs, we can set them to ground. So this is how it looks like in Proteus or in any CAD software. So we have here the two 74LS95 ICs, and we have here the inverter. So we are using 74LS04 IC. So all the clock inputs are connected to the clock source, and all our unused inputs are connected to ground. So we have arranged our LEDs in a way to easily see the direction of our shift. So our shift in is the output of this inverter, which is B in our original design. Here, this is D1. So output Q1 is connected to the input D0. Output Q0 is connected to D3 of the left neighboring SN4LS95 here. The output Q3 is connected to D2. Q2 is connected to D1. Q1 is connected to D0, and Q0 being the shift output is connected to this inverter to perform the Johnson counter operation. So let's try to simulate this. So here we can see that the shifting is coming from the leftmost, and this just switches, and this just repeats. If we change our clock to more than just 1 Hertz, then we can see a faster result here at our outputs. So for our last example, example 2, so we now design a 5-bit shift right Johnson counter, but this time using one SN4LS95 and one SN4LS76 IC. So this is a JK flip-flop. So just 1 bit plus the 4 bits here would make up the 5-bit shift right operation. And again, Johnson counter. Okay, so we now have our 74LS95 here and our 74LS76 here. So we just need one JK flip-flop to complete our 5-bit shift right Johnson counter. We need to identify which ones are at the left and at the right side of our shift register. So in this case, since we are creating a Johnson counter, so this is more convenient if we assign 74LS76 as our rightmost output because of this complemented output that we can see here. And so since we are using the shift right operation, then the direction of our shifting goes this way. So our mode must be low. we use SER as our shift input. In this case, we don't need to use the parallel inputs, so we can just simply tie them to ground. So just to temporarily label things, this must be our shift input, SER, and the shift output of our Sunfire LS95 is QD. But since we need 5 bits, then we need to connect this to our JK flip-flop, and our serial output must be coming from here. Either of the two, but since we are constructing a Johnson counter, then we need the complemented output. So the easiest thing should be to connect a D flip-flop so that we can just simply connect it to one input. But in this case, since we are using a JK flip-flop, then we need to construct this as a D flip-flop. So again, the D flip-flop has two states, 0 and 1. And this is our reset, and this is our set. For a JK flip-flop to operate as a D flip-flop, we need to consider the reset and the set states of the JK flip-flop. So which means that this is reset, this is set, and to get the reset, J must be 0, K must be 1, and to get the set output, this must be 1 and this must be 0 for J and K respectively. So you can look this up in the characteristic table. So if we want this outputs at our next state, then we need to connect J as our D input because this is the same. So that means we are going to connect QD to our J input because we need this to connect to the D input, and while J is just equal to D, then we can just connect them together. And the K input, we need it as a complement of D or the complement of J. And since we don't have a complemented output here, then we might after all need an inverter to connect that to our K input. So now this functions as a D flip-flop. And we have here the direct inputs preset and clear. We must connect them to high because these are active low inputs designated by the bubbles here at their pins. To construct the Johnson counter, we need the SOR, and we need to connect the complemented output to its serial input, which is here. So we can now remove this here, and we can also remove that as well. So this now completes our design. So this is now our design laid out in Proteus. So we have here the 74LS95 IC, the 74LS76 JK flip-flop, and we have here the inverter in order to construct the D flip-flop equivalent of the JK flip-flop. Here, take note that the clock inputs are tied together. So 3 inputs connected to the same clock source. And we are connecting mode to low since we are using the shift right operation. The unused inputs for 74LS95 is connected to ground as well since we don't need that. And the unused inputs here, direct inputs, the preset, or here in this case this is called the set and the reset inputs, we can just connect them to high. So the rightmost flip-flop is the output here of the JK flip-flop, and since we are constructing a Johnson counter, we use Q bar and connect that to the serial input here. And again, Q3 is connected directly to J, and K is its complemented value. So D prime would be connected to K. So now the JK flip-flop acts as a D flip-flop. So now let's simulate this. So now this is shifting to the right. we are switching back to 0 because of this complemented output here being shifted back in to the shift register. So now we have completed all the examples. So this is the end of lecture 3. So please answer the next exercise, which would allow you to design other types of shift registers. So if you have questions, please send us a message or an email. So thank you very much for watching.